Hello and welcome to my portion of the 2020 Vampire Workshop Talks presented by the Computational Magnetism Group at the University of York. My name is Andrew Naden, I'm a PhD student at the University of York and my work focuses on rare earth ferromagnets generally concerning the 214-1 type. Before I get started, I'd like to say that a large amount of useful information is available on the Vampire website and in the Vampire manual, both available at vampire.york.ac.uk. Before we get started, it's important to understand the input and output options available to us. Vampire has a series of input files that the program reads from at startup. These files include input, material and unit cell files, and sample input files for simulations are available on the Vampire Workshop GitHub page. As for output options, these are presented in the Vampire manual, but here I want to talk about a few that make the output data from Vampire slightly easier to understand. The output column headers option gives each of the columns a header name that is related to the input option that created it. Here we can see the input option inside the input file and the corresponding output with headers for each column of data. The ID parameter at the start of each header is related to the material or layer that data is taken from, and we'll talk more about this later. And as you can see, this still isn't the easiest data to read, but the columns are addressable by name rather than position. If we want, we can separate this data into slightly more readable columns using grep, column and less. This series of pipe commands matches all lines without comments to remove the header, pipes it to column, which tabifies the output into regular columns, then pipes it to less so we can view it with the TAC S option, which forces columns to be sliced if they would wrap to a new line. As we can see, this gives us nice regular columns where each column header is clearly separated and connected to separated from each other and connected to the data that they correspond to. Vampire can create a series of statistics from its atomistic simulation. These statistics are calculated after equilibration time steps for each run in the simulation and averaged over the length of loop time steps. This means that equilibration time steps do not contribute to the averages. The main statistics that are useful to us are presented here inside the statistics folder of the source of Vampire. The magnetization of your material, the susceptibility of the material, the specific heat of the material, and the total energy of the spins in the system. Each of these statistics can be calculated for individual materials or individual layers in a height-defined system, allowing for exploration of these macroscopic properties of varying sections of a material. This can lead to a lot of different output columns, so it's a good idea to process the output data programmatically. Python and the NumPy library are good choices for this. The magnetization of the system is calculated by summation of each of the components of each spin in the material. And we can see this here in the source code of magnetization.cpp. SX, SY and SZ are the spins of a particular atom, and MM is the magnetic moment of that atom that is defined in your input file. Once we've calculated the total magnetization in each component of the system and the total magnetic moment, we can normalize our magnetization values with respect to this total magnetic moment so that perfect alignment would be 1. Looking at the energy.cpp file, we can see that the energy of the system is a summation of exchange energy, anisotropy energy, applied field energy, and magnetostatic energy, which corresponds to the atomistic Hamiltonian that Richard presented in the introductory videos. The susceptibility is calculated using the variance in magnetic spins, as you can see here. It should be noted that this parameter is especially susceptible to time step. So if you want a reliable susceptibility value, you will need to spend more time doing computation. Thanks for listening to this short presentation. More videos like this can be found on the Vampire-Workshop YouTube page, and some useful files and presentations can be found on the Vampire-Workshop GitHub.